Okay, let's look at topic 7.9 from AP Calculus BC, and this is about logistic differential equations. Okay, well, what's that? Well, let's read through a few things. First of all, regular exponential growth and decay formulas are sometimes not realistic because they don't consider what we call carrying capacity. So carrying capacity is the maximum or minimum limit that something might grow or decay to. For example, let's say you have a population of bunnies growing exponentially. Well, at some point, those bunnies just cannot keep growing, right? Their environment has a carrying capacity based on the amount of shelter that's available, or the food that's available, or predators, or other reasons. So there is a limit, a carrying capacity to how great the greatest amount that those bunnies can grow to. So a logistic differential equation is an exponential equation that allows for carrying capacity. So this uses the same ideas from AP 7.8 with exponential growth and decay problems, except for it now is going to consider another variable, which we're going to call L, carrying capacity. So there are three primary ways that you might see the logistic differential equation modeled. And the first two are solved for the differential. So these are differential equations. They're solved for dy dt. And so you have some version of your proportionality constant, just like in AP 7.8. And then you have your value, your amount that you're looking at, the number of bunnies in the example I just said. And then your L is your carrying capacity. So what's the maximum amount those bunnies can grow to? Now, L can also be a minimum amount if you are decreasing or decaying. Now, A and B are the same equation, just written two different ways. And you really need to be familiar with both ways. You need to be able to see that if it's 1 minus y over L, then your carrying capacity is right there in the bottom. But sometimes it's written as L minus y, with that L also out front underneath your constant of proportionality. And these two numbers here, K over L, will not usually be separated for you. They'll be divided into one number, maybe a fraction or something. And so whenever you see this version B, to pick out the L, which is the most important part of this AP exam, you're going to see that it's the number minus y, the number in front of the minus y. Now letter C is the solution of the logistic model. And so it's what we would do if we use separation of variables to get the y all by itself. Now, while Unit 7 in AP Calculus does involve differential equations and finding general and particular solutions by separation of variables, you will not be asked to do that on the AP exam in just about any scenario imaginable, because it's a pretty difficult way to derive the equation for C. So what you really have to do, and probably the most important thing in this unit, 7-9, is that you memorize these three equations. And you see where the K's go, where the L's go, and so on and so forth. Now you will notice that the solution of the logistic differential equation has an extra variable b. And b is a factor found from the initial condition. It's kind of like whenever you had to find c in exponential growth and decay problems from AP 7-8 or 7.8. Okay, so those are the three. The biggest thing you have to do to prepare is to learn these three equations, to know what they are, to know where the parts are. Okay, let's read a little bit more. Number 4 here. The growth rate of a logistic model is always at the time of half the comparison. Okay, this is not worded correctly. This should say the maximum growth rate. So if we want to find out when those bunnies are growing the fastest, the greatest growth rate is always going to be half the carrying capacity. So let's say our field can hold 1,000 bunnies. Then the time that our bunnies are growing, the population is growing the fastest, will be whenever those bunnies are half of that 1,000 carrying capacity, so at 500. That's really important. This is probably the biggest thing that's found on an AP exam, different variations asking about that, and we'll look at that in just a few moments. Honestly, on a typical AP exam, you might find one question on the entire exam about logistic growth and decay models. So they're just not super common. I mean, they're common enough that they're usually there, but not one of the biggest parts of an AP exam. This is a graph of an exponential, of a logistic growth model. And you'll see that instead of just growing exponentially and continuing up, we hit this carrying capacity. And so that's the dashed line that you see there. And this dashed line is, that's the L. Okay, so I'm going to just put a big L on here by that dashed line to show that is the carrying capacity. You'll also notice that I have highlighted the place on the graph where we have the greatest growth. Now let's just think about that from a few different perspectives here. First of all, we would be really interested in learning the time that creates that point. Now the value of that point's easy. It's always half the L. And sometimes we see on an AP Calculus exam that the question is simply asking you to figure the L out of the equation and cut it in half to say, what would be the number of bunnies that occur at the time of greatest growth. And so it's just half the L. Or you might solve for the time there or something like that. You might have to, now this is an important thing to think about, you might have to find the slope right here. And of course, slope of a graph is the first derivative. And the first derivative goes back up to the top of the screen here to our two logistic differential equation models. So you would need to plug in half of L into one of those equations, whichever one works best for you, to find out what the slope would be at that point. So those are all things that you need to do there. I think it's also worth mentioning one more thing on this graph, two more things actually. One is that this point, right, half the carrying capacity, that's also a point of inflection, right? So that's a place where the second derivative is going to equal 0. Just kind of thinking about the way first and second derivatives work with graphs. The other thing to understand is that this is a model of logistic growth. We can decrease, we can be going down. And so if L is still our carrying capacity, then we would be going down to it like this green graph, something like that. Okay, so we would be approaching the carrying capacity from the top, and as we move through time from left to right, we would be decreasing and coming down to that carrying capacity. So some stuff that I pointed out on the graph, I'm going to read it here. In the logistic graph above, notice that L is 10. The moment of greatest growth is at t equals 1.39, and y is equal to 5, or half of L. You could calculate the rate of change at t equals 1.39 using the formulas above, and that's what I circled and showed you. And then an idea about decay here. If the logistic equation represents decay, then the L will be at the bottom of the graph, and K will be the opposite sign in the equations. Now, this is really important as well. K is going to be the opposite. Changing the sign of K is what gives you decay. Now, be careful, because up here in our equations, in the differential equations, K is positive. And this positive K represents logistic growth. However, be really careful. In the solution equation, K is negative, and that represents growth. And so it's really important to see and understand what kind of K you're looking at. Because one type of AP Calculus exam question we've seen in the past is a question that says, which of these equations models logistic growth or increasing logistically or something like that. And so you've got to know, okay, are they giving me a differential equation? Are they giving me the solution of the differential equation? And what's K supposed to be for growth in both of those? So one more time, in the differential equation, a positive K means growth. In the solution to the differential equation, a negative K means growth. If those K's are opposite signs, then it's decay or decreasing. Okay, so what might you need to know on an AP exam? First of all, what I just said, you might need to know which of several models, which of several equations is a logistic model. Kind of just talked about that. You might need to find the carrying capacity in a version of one of the above equations. And I say in a version of because sometimes the AP exam will do something like this. Instead of a straight out the way that we saw it above, they might tell you that this is a logistic model, and they might ask you for the carrying capacity in that. Well, if you look at the equations from above, we would find out that this looks like a letter B here, K over L times Y times L minus Y. So let me just write that, K over L times Y times L minus Y. Now, this whole front stuff is, well, that's going to be, some kind of fraction times Y, something weird going on here, and we don't see that here. There actually would probably be a Y here. But we don't really need to focus so much on that as much as we need to get the L minus Y. So a wrong answer to this would be saying the carrying capacity is 20 or 200, because what we know is that it's supposed to be carrying capacity minus Y. Well, there's an extra number here with Y, an extra 20. So what we'd actually have to do is we'd have to factor out that 20 to the front. So I'm going to take a 20 out of all of this, and 200 divided by 20 is 10 minus Y. And so in this case, our carrying capacity is 10. So that's a fairly common type of question that you could see on an AP exam, where they take one of the three equations that you need to memorize and just kind of maneuver the numbers around a little bit so that you've got to pick out the L, the carrying capacity. A few more things. First of all, we kind of talked about this already, but you might have to find the time or the Y or the rate of change where the carrying capacity is at its greatest rate, so L divided by 2. This is a fun one. You might need to find the limit of the equation as time goes to infinity. That sounds really hard, but that just would equal the carrying capacity, right? As time goes to infinity, your population should be nearing the carrying capacity. So actually a pretty quick answer, as long as you can pull out the L. Again, the L might not be presented in a normal way, so you might have to find the L. Now, this is letter E's. Let's read through it. There's a lot to read here. You might need to find the solution form, so that's the C equation we had on the first page up above. You might have to find that solution form from the differential equation form. But you shouldn't have to ever use separation of variables to figure it out. So what you might, here's what we could see, is you could see a differential equation that's actually kind of like this one up here, where it's not normal, and you have to manipulate it. And then once you manipulate it, you can say, okay, now I see my L and my K. If my L is 10, my K is going to have to be 200, because that's the only way that we can divide by 10 to get to 20. So now I have an L and now I have a K. Now I can write that into the solution form. So what you need to do is memorize the parts of the differential equation and the solution and see how they match up. So back up to the front. Again, the most important thing you can do on this lesson is memorize those three equations. The differential equation you're given might look slightly different from the one shown above, and you might have to manipulate it to find the correct L and K, just like we just did. And then a few things you might have to do that are kind of like stuff that you would have practiced in the previous AP lesson 7-8. You might have to solve for B, so you might find that B value given some initial condition. So you're going to use the solution form, equation C from above, and you're going to plug in your initial condition. Probably time would be 0 and Y would be some value, maybe like 100 rabbits, and solve for B in that case, just like you did in Calc 7-8. And then you might have to also then solve for the K if you don't know the K. Usually that would be after you're given the B. This could be like an open response type question on a calculus exam, and they give you a new ordered pair. This is all very similar to stuff that you had to do on 7-8. You had to find the C, and then you had to use that to find the K, and so on and so forth. And then finally, you could be asked to take your equation, estimate a value in the future. How many rabbits might there be after 12 years or something like that. So there you go. That is AP Calculus 7-9. This is a BC topic, and hopefully that helps.